let's look at a couple applications of these geometric operations. So one thing, so we know how to reflect across one of the coordinate axes, but what if we want to reflect across some other line, right? There's no convenient entry in our matrix for lines that aren't the coordinate axes, so that's a little unfortunate. But what could we do? I mean, so if we want to reflect across this line, this is the line y equals mx, this line makes some angle theta with the x-axis. In fact, this angle is actually, it's arctangent. It's actually arctangent of m. So how could we figure out a matrix for this linear transformation? So let's do this. We know how to do a reflection if the line is one of the coordinate axes. So what we could do is we could start out just by rotating by minus theta so that the line we want to reflect across is actually lying across the x-axis. And then we could reflect across the x-axis. Right? That will achieve the reflection across the line. But then we need to rotate again to get our line from the x-axis back to this line that we started with. So then we want to rotate by the angle theta. So we're sort of tipping the line that we want until it's convenient, doing the reflection in the convenient place, and then tipping the line back to where it started. And we know the matrix for each of these, so rotation by minus theta is cosine minus theta minus sine minus theta, sine minus theta, and cosine minus theta. Reflection across the x-axis, that's 1, 0, 0, minus 1. And then rotation by theta is cosine theta minus sine theta, sine theta, cosine theta. Now for these minuses, right, cosine is an even function, so this minus doesn't make any difference. And sine is an odd function, so the minus on the outside is the same as, having a minus on the inside is the same as having another minus sign on the outside. So this minus sign actually cancels that minus sign, and this minus sign here actually becomes a minus sign on the outside. Okay. Well, now let's do some matrix multiplication. So let's multiply these two. We get cosine theta, sine theta. And then for the second column, we get sine theta minus cosine theta. Okay, and then our last matrix is cosine theta, sine theta, minus sine theta, cosine theta. Okay, and now we can multiply, so we get, let's see, cosine squared theta minus sine squared theta. Here we get sine 2 sine theta cosine theta. Here we get, let's see, minus 2 sine theta cosine theta. And here we get, looks like it's going to be sine squared theta minus cosine theta. Okay, so what are all these things? Well, remember theta was arctangent m, right? So that means if we have theta in a triangle like this, we can put m on this side and 1 on that side, and then the right, because then in this right triangle, tangent of theta is m, it's m over 1, then the hypotenuse is square root of 1 plus m squared. And now that we have a picture of theta, we can actually evaluate all of these trig functions. So cosine squared, well, cosine is 1 over this square root, so the square of that is 1 over 1 plus m squared, minus sine squared. Sine is m over the square root, so the square of that is m squared over 1 plus m squared. For 2 sine theta cosine theta, that's 2 times 1 over the root times m over the root, so 2 times 1, sorry, sine theta is m over the square root, and then cosine theta is 1 over the square root. Okay, down here we get the same thing but with the minus sign, so minus 2 times m over the square root times 1 over the square root. And then in the bottom right, sine squared is m squared over 1 plus m squared minus cosine theta is, this should be squared, 1 over 1 plus m squared. And now, right, we can simplify all of this stuff, and we get 1 minus m squared over 1 plus m squared. We get, in this entry, we get 2m over 1 plus m squared. Down here we get minus 2m over 1 plus m squared. And in the bottom right, we get m squared minus 1 over 1 plus m squared. Now you can see all of these entries have a 1 plus m squared in the denominator. So we could actually pull that out front as a scalar multiple. So this is 1 over 1 plus m squared times the matrix 1 minus m squared, 2m minus 2m, and m squared minus 1. All right, so there we go. Pretty nice. Pretty nice that we can get a matrix for this more complicated geometric operation just by using our basic operations of rotation, reflection, and shear, although we didn't use shearing this time. Let's look at one more application. So let's think about rotating by a sum of two angles. So if we write down the matrix for rotation by a sum of theta and phi, right, we get some cosines and sines. We get cosine theta plus phi minus sine theta plus phi, sine theta plus phi, and cosine theta plus phi. But rotating by an angle theta plus phi, that's the same thing as rotation by phi and then rotation by theta. Or, yeah, let's write it that way. So what we can do is write the matrix, if we're going to do rotation by theta afterwards, we need to write that matrix first. And then rotation for matrix by phi, write that one first. So what we can do, right, rotating by a sum of two angles, that's the same as rotating by one of them and then rotating by the other one. Right? That's just going to add up the angles. But we can write the individual matrices. So the matrix for rotation by theta is cosine theta minus sine theta, cosine theta. And the matrix for rotation by phi is cosine phi minus sine phi, cosine phi. And then we can just do this matrix multiplication. In fact, I mean, we could do the whole thing, but I'm really only interested in the first column. You'll see why in a second. So when we do first row times first column, we get cosine theta times cosine phi minus sine theta sine phi. Okay, and then for the second entry in the first column, we get, right, second row times first column, we get sine theta cosine phi plus cosine theta sine phi. Well, these matrices both represent rotation by theta plus phi, so these matrices have to be equal. In particular, that means that cosine of theta plus phi has to be equal to cosine theta cosine phi minus sine theta sine phi. And sine of theta plus phi has to be equal to sine theta cosine phi plus cosine theta sine phi. In other words, what we just did is we discovered the addition formula for sine and cosine. So, when you first learn about the addition formula for sine and cosine, this particular combination of sines and cosines, it seems sort of crazy and arbitrary. But now we understand that the reason that these sines and cosines are mixed up in this particular way is because this is actually just matrix multiplication. That's where these come from. So that gives a really good explanation for why exactly the sum formula for sine and cosine are what they are.